One of the goals of this class is to be able to calculate the work done to move a particle against a force field. In order to do that, we need to be able to describe the motion of a particle in space. So we're going to use the tools that we know from calculus, derivatives and integrals, and also the tools that we've developed, the cross product, the dot product, vectors, and parametric equations. Training. I'm going to make a math video. Here's the new notation that we're going to use to describe the position of a particle in space. So R of t is going to be the position at time t, v of t is going to be the velocity, and a of t is going to be the acceleration. They all depend on time. And you learned in Calc 1 that the derivative of position is velocity. So dr dt should be v of t. And then you also learned that the derivative of velocity is acceleration. So dv dt, which is the second derivative of the position, should be the acceleration. But according to Isaac Newton, force is equal to mass times acceleration. So since we are using vectors as a model of force, we also need to use vectors as a model of acceleration. So we're also going to need to use vectors as a model for velocity. And then this means that we're going to need to use vectors as a model for position. So the big picture philosophical approach to this is that vectors are a model for force, but then Calculus 1 tells you that whatever you're using to model force, you also need to use to model acceleration and velocity and position. So what this means is we have a vector, and the coordinates of the vector represent the position of a particle, and those coordinates depend on time. So I'm just going to name those coordinates x and y and z. So the question is, how do we define the limit of the position of a particle? Well, it makes sense to me that whatever the x coordinate is getting close to, and whatever the y coordinate is getting close to, and whatever the z coordinate is getting close to, should also be what the particle is getting close to. So we define the limit of the position of a particle to just be the limit of all of the coordinates. Okay, so the way that we define the limit of a vector that has functions in the coordinates is just to take the limit of each of the coordinates. So that has kind of a cascade effect on all of the other basic calculus operations. Since the derivative is defined in terms of limits, we are also just going to take derivatives of each of the coordinates. And likewise, because integrals are defined in terms of limits, then we're just going to integrate all of the coordinates. I put here the definition of the derivative. It probably is important that you remember these specific symbols, and I'm going to take a minute now to go over what the graphical interpretation of this is. So how can we interpret dr dt? Well, the definition of dr dt is as a limit of a difference. So I want to just remember graphically what the difference of vectors looks like. So I'm going to draw two vectors here, and I'm going to make this one v and this one u. And I'm trying to understand what u minus v is. So the first thing I'm going to do is just make v negative. So that's easy. I'll just take this picture, slide it over here. But now, since I'm not doing v, I'm doing negative v, I will reverse the direction of v. Okay. And now, the way that you add vectors, so now I'm just doing u plus negative v, is you just start at the initial point of one of the vectors and you go to the final point of the other vector right there. So this is the vector u minus v. So let's bounce back to the motion of a particle in space. So I've drawn the path that the particle is taking, and then the definition of the derivative is this limit of delta r over delta t. And what we just worked out here was how you subtract vectors. So I've drawn the position of the particle at time t0, and I've drawn the position of the particle just slightly forwards in time. We've increased time by some very small amount called delta t. And then, as before, when we calculate the difference in r, we're going to get that vector right there. Now imagine delta t going to 0. So what that means is that each of these arrows are now going to take a smaller and smaller step forward. So as I pull that second point back closer to the first point, I am going to end up with a red line that is perfectly tangent to the curve. If r was moving along the path faster, then each one of these red lines would be longer as I was going in and taking the limit. Therefore, the derivative of r is tangent to the curve, and also the magnitude of the derivative is the speed that the particle is moving. Before we move on, I want to have a look at a computer-generated graph of the motion of a particle in space. So I'm here in CalcPlot 3D, and the way that I built this graph is I just went to Add to Graph, and I selected a space curve. And then I put in these functions. I'm using x is t cosine t, y is t sine t, and z is t. And then I scaled the whole thing down by a factor of 1/10, so it would just fit nicely on the graph and these arrows don't get too big. So this particle is essentially moving in a circle in the xy plane, except since I put a t here in front of the cosines and sines, as time increases, the radius of this circle is getting bigger. And then the z coordinate is just moving up linearly at a rate of 0.1 times however much time has elapsed. So the z coordinate is just driving straight up, and the x and the y are kind of making a circle that's getting bigger and bigger. So I'm gonna I'm gonna animate this particle, and the computer's going to draw a blue arrow. That's r of t. That represents the position of the particle at time t. Now, if you click this little cog, you can have the computer graph other things as well. We are going to go on to learn what all of these things are. I'm going to start by putting in the velocity vector at time t. So this tells us the direction that the particle is going in. You can see it's kind of always moving around the circle and also kind of moving up a little bit. You see as we come around here, the particle is moving along the red path, and also it's kind of going up a little bit. And now if I add the acceleration vector as well, that's going to be the green arrow right there. You can see that the particle is turning, so it's kind of accelerating towards the inside of the spiral, and also that green arrow, it isn't going up at all, right? Because the particle is just moving up at a constant speed. I think if I changed this to squared, is this going to make it go out of the top of the graph? It is. Maybe I'll make this 0.01. Okay, now we're back here. So now this green arrow should also be pointing up a little bit, because now I've made the particle go faster and faster and faster in the z direction. So this is kind of what's going on with this. You know, take some time out of your life to just drop in some of these graphs to CalcPlot 3D. It's really fun, especially if you use trig functions in all the coordinates. I'll just do another one here. So, you know, you can make a lot of really interesting graphs this way. Load up CalcPlot 3D, and anytime you're doing one of these homework problems, it's probably good to just have a look at what your path actually looks like in space. Okay, let's do an example where we actually go through the mechanics of these problems. I've got r of t, and I'm asked to find the velocity and the acceleration at time 0. So this is really just basically a Calc 1 problem. Sometimes my students will joke that Calc 3 is just like 3 Calc 1 problems. It's kind of true sometimes. So v of t, all I'm doing is literally taking the derivative of each of these coordinates. So 4, 12t, and 3. So at time 0, I get 4, 0, 3. Now, a of t is going to be, the derivative of a constant is 0, and then 12, 0. So a is actually constant for this particle. So at time 0, a is always 0, 12, 0. So, write v as a product of its length and direction. Okay, so let's do that. So the magnitude of v, remember that this is also the speed. Just kind of a good mantra to put into your head that the derivative is the velocity, the magnitude of the derivative is the speed. So in this problem, I'm going to do the square root of 4 squared plus 0 squared plus 3 squared. So 16 plus 9 is 25. So this is 5. So I can write v of t, v of 0, as 5 times 4/5, 0/5, and 3/5. So I've done it. I've written v as a product of its length and direction. Just as a quick observation, because this does actually come back later, this right here, remember the velocity is tangent to the path, and it also, this vector here has magnitude 1. So I would like to call this thing the direction of motion. Later, we're going to go on to use the letter T for tangent when we describe this object, a unit vector that's pointing in the direction that the particle is moving. It's really common for students to be asked to find the angle between the velocity and acceleration. So let's go through those mechanics as well. So when we're asked to find the angle between vectors, we're going to have to use the dot product. So remember that v dot a is equal to magnitude v. We already worked that out. That's actually 5 times the magnitude of a. You can actually just see that empirically over here, right? If you just look at it, the magnitude of a in this problem is going to be the square root of 0 squared plus 12 squared plus 0 squared, which is 12. So we know that, and then cosine theta. So let's just calculate this dot product, and we should be able to end up with theta pretty quickly. So in this problem, v dot a is going to be 403 dot product with 0, 12, 0. So when we do our little sum of the products trick, I'm going to do 4 times 0, 0 times 12, and then 3 times 0. So in this problem, the dot product of these two vectors is 0. So we're already done, right? We know that in this case, v and a are orthogonal vectors. But let me just write that down. So technically what we know right now is 0 is equal to 5 times 12 times cosine theta. So you divide both sides by 60. So 0 is equal to cosine theta. So theta is equal to either pi over 2 or 3 pi over 2, but I'm going to keep all of the angles between 0 and 180. So in this case, at this specific time, these two vectors are perpendicular to each other. This was kind of a fluke thing, though. This was a special thing. In general, v and a are not going to be perpendicular to each other. I just wanted to check my claim that in general velocity and acceleration vectors are not perpendicular to each other, and usually they're not. You can see here, I pulled up Calplot 3D. I put in our space curve, and I'm using a time between -1 and 1. The time that we're concerned with is time 0. And you can see here that the velocity and acceleration vectors are not at a 90-degree angle. The black vector is the velocity, and the green vector is the acceleration. So as I go forwards in time, we kind of get closer and closer to that vertex of that parabola there, and then right at time 0, you can see that they do make a 90-degree angle, and then the angle gets more acute as you go forwards in time, and then back over here in negative time, the angle is kind of obtuse. So it's really a special thing that happens when velocity and acceleration are perpendicular to each other. Actually, that's kind of a fun puzzler if you want to think about what kind of motion should have velocity and acceleration always perpendicular to each other. So there's a little food for thought. So it's tempting when you start taking derivatives of vector valued functions to feel like this is a process that always works and is kind of bulletproof, but it's not. It is absolutely possible to have a path and the tangent vector to not exist. I've got one here that is actually in the plane. So let's have a look at that. I've chosen x is equal to t and y is equal to 2/3 t. So just really fast, if y is equal to, sorry, I said it wrong, but t to the power of 2/3, then dy dt is going to be 2/3 t, and you have to subtract 1, so you're going to get to the -1/3 power. So this is basically like 2/3 times t to the 1/3 power. So this is undefined when t is equal to 0. So let's look and see what the graphical interpretation of that is. So as I slide this particle, the time forwards, and the particle gets closer and closer to 0, you can see that it is moving faster and faster and faster, and the tangent vector is getting more and more vertical. And then when I get to the other side of 0, it pops out the other side and is pointing in the other direction. So actually right there at 0, there is no velocity vector. It's undefined. So this path isn't smooth. I like to imagine when I'm talking about paths that aren't smooth, I like to think of it as this is a roller coaster that I would not ride. Right? I mean, if you were on this roller coaster, you'd be going faster and faster and faster and faster and faster. And I don't know what happens right there, but it is not going to be a comfortable experience. So that's where we get that word smooth from. I can pretty much guarantee that write the equation of a tangent line is a question that's going to appear on a Unit 1 test in almost every Calc 3 class. So what do you need in order to write the equation of a line? You need a point on the line, and you need a vector that points in the direction of the line. So r of t is all of the points on the path. So to get a point on the line, you can just plug the time into the position function, and that'll give you the point on the line. And then remember that the velocity is always pointing in the direction of motion. So when we find the velocity, then we can just plug time into that velocity, and that will give us the direction of motion. So for this problem, r of 0, this should be easy. So the sine of 0 is 0, so 5. Now, when I plug 0 into this, I'm going to get 0. And then the cosine is 1, so this is going to be -4. Now, this is 2 times e to the 3 times 0. So 3 times 0 is 0, and e to the 0 is 1. So this whole thing is going to be 2. Now, v of t is going to be, the derivative of sine is cosine. So 5 cosine t, so used to thetas. Then 4t cubed plus 4 sine t. And then chain rule is going to give me 6e to the 3t. So v of 0, the cosine of 0 is 1, so this is going to be 5. And then 0 here, and then when I plug, just as before, when I plug a 0 in for that t, I'm just going to get e to the 0, which is 1, so this whole thing is going to be 6. So now I'm basically just using that the equation of a line is just the vector times time plus the initial position. So let's do it. We've got our answer here. X of t is going to be 5t plus 0. I'll go ahead and use it. This is where if you're trying to follow the pieces, this is where they go. Okay. Now, y of t is going to be 0t minus 4, and z of t is going to be 6t plus 2. Okay, fantastic. So these are some good examples of motion in space problems. In the next lesson, I'm going to basically go over some example problems where we go the other direction, where instead of taking derivatives, we're taking integrals.